Hey everybody, welcome back to what I'm going to call lesson 6.5. The state of Alabama required that you also have a solid foundation in converting metrics units, and therefore the textbook company created a whole special lesson, Alabama Lesson 1, just for you guys, so that you'd have what you need in order to be ready to go on into the next level of converting metric units. You can see our objectives today. Students will convert metric measurements to both metric and customary units. Now going from one to the other, that gets pretty interesting. And we have got one new vocabulary term to go with that one, and it is dimensional analysis. This is defined as a process of including units of measure as factors when you compute. You can use this to convert from one unit to another. Now, starting up our lesson here, we're going to find that this one is actually suggested pacing only for 45 minutes, meaning this is the first lesson we have come across in this book that they are saying should only take 1 day to cover. So, with that said, let's get started. The metric system, known officially as the International System of Units and abbreviated as SI from the French Le Système International des Unités, yeah, I don't speak French, is the most widely used system of weights and measures in the world. The metric system was created by scientists and was designed to be simple, unlike the American Standard System, using only 7 base units, like meter, gram, liter, and so on. It follows the decimal number system, so each metric unit increases or decreases by a size of 10. I would refer to that as a factor of 10. The 7 standard measurements are defined by fundamental constants of nature that can be reproduced anywhere at any time. Until recently, the mass of Lagrange K, a cylinder of platinum and iridium, was the official definition of the kilogram. In 2018, the General Conference voted to redefine the kilogram so that it was no longer based on an artifact. So apparently the Lagrange K was an artifact, and where it was a cylinder of platinum and iridium, I guess they didn't like it being based on something historical, so now it's based on something new. Moving to our next slide, Lagrange K has a measure of 1 kilogram. What information would you need to know how to convert this into grams? What methods could you use? Well, you'd need to know how many grams were going to be in a kilogram, right? And then you could easily convert it from kilograms to grams. What methods could you use? Well, you could use a bar drawing, but I just don't really like that, particularly considering there'd be 1,000 little bars in it going from a kilogram to a gram. I think that using the ratio method would be a lot better choice to use. Dimensional analysis, as we talked about already, is the process of including units of measure as factors when you compute. You can use dimensional analysis to convert from one unit to another. Watch the dimensional animation and see how to use dimensional analysis to convert units. So we're going to take and pause it right here and let you all watch that video. Here we go.
Convert 6 pints to fluid ounces. Since you don't know the unit ratio used to convert pints to fluid ounces, you can convert pints to cups first. 1 pint equals 2 cups. So the unit ratio is 2 cups to 1 pint. Multiply 6 pints by the unit ratio. Divide out the common units, pints, so that cups is the remaining unit. Then multiply. 6 pints is equal to 12 cups. Next, use the unit ratio 8 fluid ounces to 1 cup to convert 12 cups to fluid ounces. Divide out the common units, cups, so that fluid ounces is the remaining unit. Then multiply. 12 cups is equal to 96 fluid ounces. So 6 pints is equal to 96 fluid ounces.
Now I know that video was a very quick and simple instruction, and we're going to go into a lot more detail on how it works. What I did want you to get out of it was that unlike when we did lesson 6 where we didn't worry about carrying the units, now you're going to carry the units all the way through. And they made a lot of leaps in understanding for you, and I'm going to work real hard during this lesson to fill in those leaps of understanding so you have a better grasp of how it all works. So, it says, in the animation, 6 pints is converted to cups. Explain why the pints in the denominator of explain why pints is in the denominator of the conversion ratio. And to explain that, I'm going to take a picture of this one, and then we're going to rewrite it in a way that makes a little more sense. So here we are. I've taken my screenshot, but before we talk about this, let's talk about something different. Let's just talk about simplifying fractions themselves. So what I want to do is I want to take the fraction that we're going to have of 6 over 8. Now, this has nothing to do with this up above. I'm just laying a foundation for what's going to happen. If I was to factor these two fractions out, 6 is the same thing as saying 2 times 3, while 8 is the same thing as saying 2 times 4. The 2's would divide each other out, saying 2 divided by 2 is 1, 1 times 3 is 3, and 1 times 4 is 4, giving you the 3/4 for your simplified fraction. We're using that same concept here to answer the question we've got going on in the problem above. So what we're going to do is I'm going to rewrite this now, where I have 6 pints over 1 times 2 cups over 1 pint. And the question was, why is a pint in the denominator of the conversion ratio? That's this one. And remember, your denominator is down. The denominator is the bottom number in your fraction. It is down. So why do we need pints in the bottom? For the same reason that we had those 2's in the bottom earlier, because now the pint divided by pint is going to be 1. In fact, let me just go ahead and show you how you could multiply that out. You could say 6 times 2 is equal to 12 times pint times cups divided by 1 times 1 is 1 times pint. I know that looks a little weird, but watch what happens now. Pint divided by pint is 1, and that means that 12 times 1 is 12 cups over 1 times 1 is 1, also known as 12 cups. The reason the pint has to be in the bottom is so it will divide out with the pint in the top. And we're going to practice more of that, so if you're a little confused still, be patient. You're going to get it. Now this table shows the ratio relationships for metric unit conversions, where your 1 metric unit is going to be your base unit. Maybe it's grams, maybe it's meters, something of that nature. And then if you're going to smaller units, milli would be 1/1000th of a gram, say. Centimeters or centigrams would be 1/1000th of a 1/100th of a gram, and decagrams would be 1/10th of a gram. Meanwhile, over here, a decagram, I think this is deci and then decagram, would be 10 grams. A hectogram would be 100 grams, and a kilogram, that's going to be 1,000 grams. Now, on those, the ones you're going to see most often is the milli, the centi, and the kilo. You don't really see the deci, the deca, or the hecto very often. Ratios for metric conversions can be found by reading the columns in the table. For example, the first column shows that 1 metric unit is equal to 1,000 milliunits. This means that 1 meter is equal to 1,000 millimeters. A liter is equal to 1,000 milliliters. A gram is equal to 1,000 milligrams. Talk about it. Compare milligrams to kilograms. Well, a milligram is 1/1000th of a gram, while a kilogram is 1,000 gram. So this one you have 1 over 1,000 in the milli, and the kilo you have 1,000 over 1. Some countries, actually some of the most commonly used metric conversion ratios for length are shown above or below. You have meters to centimeters is a 1 to 100 ratio because there's 100 centimeters in a meter. Meters to kilometers is a 1,000 to 1 ratio because there's 1,000 meters in a kilometer. And meters to millimeters is a 1 over 1,000 because 1 meter is equal to 1,000 millimeters. A conversion ratio is a unit ratio if the first quantity is compared to 1 unit of the second quantity. The ratio meters to kilometers that you see right here, that's going to be a unit rate. It's the only unit rate they gave us there because you're comparing the first quantity to 1 in the denominator. Next, pause the recording and answer the 2 questions that are following it. Alright, your first question said, what is the unit ratio for centigrams to grams? Well, I'm going to take and I'm going to go back and look at a screenshot I took. Grams is my base unit. Centigrams, there's 100 centigrams in 1 gram. So we're going to set that up as a fraction. Let's see if I can do it right. We're going to use our fraction option, which is right here. And I'm going to say that we're going from centigrams 100 to grams, which is going to be, oh, nope, trying to get it to work right, 1. We're going to accept that. And then what is the unit ratio for milliliters to liters? Once again, my milli is going to be, there's 1,000 milliliters to 1 liter. So we're going, in this one here, your milliliters is your first number, 1,000, your liters is your second number, 1, hit accept, check our answers, and excellent, we got them both right. Compare metric unit ratios with customary unit ratios. How are they like and how are they different? Well, they're alike because you're still moving from bigger to smaller and smaller to bigger. They're different because with the metric system, everything's base 10. And it makes it so much easier to work with. Base 10 meaning tens, hundreds, thousands, and things of that nature. You can use reasoning about ratios or dimensional analysis to convert between metric units. Suppose you need 400 grams of rice for a recipe, and rice is sold by the kilogram. You can convert 400 grams to kilograms to determine how much rice to buy. And here they have a problem set up that is something that you should recognize as something we've worked with before. Now they're not doing real good dimensional analysis where they're canceling their units out, but the problem is very similar to what we've done before. So you can see how they have it set up here, just like we've done before. They say there's 1,000 grams is equal to 1 kilogram. They need 400 grams, so they took and said, well, gee, what am I going to do to 1,000 to get it down to 400? And they made some really big steps of voodoo math here where they magically came up with that 2.5. Where on earth did 2.5 come from? This is where it came from. They took, oh, my pen stopped working. Give me a second. See if I can get it light up again here. They took 1,000 and they divided it by 400. Now I've shown you a trick before where I said that you can do some decimal bouncing, where I've got 2 zeros here, 1, 2, and I have same 1, 2 there. So I could rewrite that problem as 4 divided into 10, which is a lot more doable for me. From here, I'm going to say, well, how many times does 4 go into 10? That's going to be 2. 2 times 4 is 8. That's going to leave 2 left over. Annex in my decimal and my 0. The decimal goes up, the 0 goes down. How many times does 4 go into 20? It goes 5 times. 5 times 4 is 20, and that leaves nothing left over. And that 2.5, young ladies and gentlemen, is where this number came from. So, if they took 1,000 and divided it by 2.5 to get 400, that means for this level here, they need to take 1 and divide that by 2.5. And when they do, we're not going to waste time doing the math, but when they do, you get that answer right there, 0.4. And that is where the 0.4 came from. In our Talk About It section, when converting from smaller units to larger units, do you think that the number of larger units will always be less than the number of smaller units? What do you think? Pause the recording, write down your answer in sentence form, and we'll come back and look at it. Alright, did you get it done? The answer to that is going to be, yeah, because you can see grams are smaller than kilograms, and we went from 400 grams down to 0.4 kilograms. That means that the number of the larger units is indeed going to always be less than the number of the smaller units. Moving on to our next slide. For this one, we're going to use real live, honest-to-goodness dimensional analysis, which is the way I honestly prefer doing these, because for me it makes a lot more sense than the way that they've been doing it, and I think you're going to find it's easier. So they've got the problem set up here where they said they started with 400 grams and they're multiplying it by the conversion factor, 1 kilogram over 1,000 grams. Now I'm going to take my screenshot, and the first thing I'm going to do with it is I'm going to rewrite this part in a part that makes a little more sense to me. I'm going to say 400 grams over 1, change it to a fraction. We're going to use a dot symbol for multiplication times our conversion factor that says 1 kilogram over 1,000 grams. Now your textbook divided out the grams here, which doesn't look quite as clean as if I do it here, because I've got a true numerator and denominator in this one. I'm going to change my pen color. I'm going to say grams are going to divide out. You could say that gram divided by gram is 1. And the idea behind that is if I had 2 divided by 2, that would equal 1. If I have 3 divided by 3, that would equal 1. Therefore, it stands to reason that if I have gram divided by gram, that is going to equal to 1 as well. And that is why these grams are able to disappear, is because we're dividing them by 1. Now I'm going to erase all this stuff here, and then we're going to come back in and start writing again. From there, your textbook did some magic voodoo stuff, throwing down the 0.4 kilograms, and they kind of sort of showed you, but they really didn't. So let's look at what actually happens there. The grams are gone, so I have 400 times 1, which is equal to 400, and the kilograms are still there. And then I have 1 times 1,000 for my denominator for 1,000. So what we've got is 400 divided by 1,000. Now you could do that as a long division problem where you put the 400 in the house, the 1,000 outside the house, because remember your first number always goes in the house, but I got an easier way. Anytime you're dividing things where you have zeros on the end, you can just take and magically go boom and boom, and now we have that listed as 4 kilograms is equal to 4 tenths of a kilogram. That's easier for me to divide, so now I'm going to take 4 divided by 10. 10 goes into 4 0 times, X in your decimal, your decimal goes up. 4 goes into 40 4 times, and 10 times 4 is 40 with nothing left over. And that is the reason you get 0.4 grams, 0.4 kilograms that you see right here in the answer. The final part says either method, using either method, you still get the same answer of 0.4 kilograms. I personally really prefer using this method over using the other. Once you get used to this, I think you're going to like it better too. Moving forward. In France, drinks are almost always sold by the centiliter, with 50 centiliters being the most common size. A case of 12 bottles of water contains 600 centiliters, and we want to know how many liters of water are in the case. So what do we need to know? Well, first off, what conversion ratios can you use to solve this problem? Now, first thing I want to point out here is that centiliters are 1/100th of a liter. There's 100 centiliters in a liter, and that's going to be important for solving this problem. So what conversion ratios here we're going to use? We're going to use 100 centiliters for every 1 liter. And using the equivalent ratios method is going to look like this. Let me get my screenshot. Now for the screenshot, they have all the answers already put in, but we're going to look at where it all came from. Remember, this is what we would consider showing your work, so you'd have to show something like this if you wanted to get credit. So, get my marker going, pick out a pretty color like red, and I can see, first off, we have our conversion factor. We have 100 centiliters for every liter. And that is equal to, well, we know there's 600 centiliters that they sell, and we want to know how many liters it is. So they ask themselves, 100 times what number? 6 is equal to 600, and that allows them to say, well, great, then that means 1 times 6 is going to equal to 6, and that is where they got their answer right here, saying that 600 centiliters is equal to 6 liters for a final answer on that one. Go back over where we have it, skip on to the next thing, and we're going to do the same exact problem, only this time we're going to use dimensional analysis. Now this is how they wrote it out, and once again, I really don't like how they're writing it out here because it doesn't make as much sense. So instead, I'm going to write it as 2 fractions, 600 centiliters over 1 times 1 liter over 100 centiliters. Now with that, we can take and do our dimensional analysis. Our centiliters, let me change my color, divides each other out. And we can also do some other simplifying here if you're good, but we're not going to do that. We're just going to multiply. That gives me 600 times 1 is equal to 600 liters divided by 1 times 100 is 100. Now remember that trick I showed you with the zeros? Dividing each other out. That leaves me with 6 over 1, also known as 6 liters. And that is where they got their final answer that you can see over here. They did the same thing. They did theirs just as it wasn't as pretty as mine, and they ended up getting the same answer you can see right here of the 6 liters. Either way you go, you get the same answer. We're going to pause the recording here and restart with part 2 in just a minute.